much. That was a lovely introduction. I really appreciate it. And it's delightful to be here, particularly giving this talk at this observatory where so much of astronomy began. And that's where I want to start this talk. There's a direct connection between Mount Wilson and the Giant Magellan Telescope, not just in spirit, but in a lot of key technology and for Carnegie observatories, as you just heard. So what you see here is the Hooker telescope, which was finished in around 1920, and it was the largest telescope in operation for astrophysics at that time, actually the largest telescope period. In about 1950, it became the second, it was no longer the largest telescope when the Hale 200 inch was complete. And those two were the primary tools for discovery used by the Carnegie Institution and the scientists, the astronomers there, until the skies in California became bright due to the cities, so light pollution became an issue, and it was appreciated that really it was going to be critical to find a site where Carnegie could continue with dark skies. So the Carnegie observatories, the institution, developed Las Campanas Observatory in Chile. First with the 40-inch, and then soon after that with the 100-inch telescope, completed in around 1970, which you see here. And in around 2000, the twin Magellan telescopes were added to the family, and you see those here. And that was in partnership with 4 other universities in the United States that helped to develop and now operate those telescopes. And when I hit return again, you're going to see why the Carnegie Observatories moved its base of scientific operation to the Atacama Desert and why that was so critical. It is one of the best locations in the world for ground-based astronomy. It has exquisite dark skies. It has an arid climate. It's at high altitude, and it's at the western edge of a continent, which makes for very smooth airflow over the observatory, which helps to reduce the blurring of stars or any objects when you're looking from the ground. And that is why we are now building the Giant Magellan Telescope at this same site. And here you see all of those telescopes roughly at scale. And of course the Magellan telescopes are not actually going to be on the same summit. They are actually roughly back here somewhere on one of these hills in the background. But if this image does not impress you with the scale, let me try again with this one. So here is the Giant Magellan Telescope in a location that probably means more to you. It's going to be a roughly 25 and a half meter telescope, 25.4 meters. The telescope itself is 15 stories tall, which is about 48 meters. The enclosure that houses it is 22 stories tall, and of course that building has to rotate so that the telescope can point anywhere in the sky. And if this image doesn't give you a sense of the challenge of building this telescope, really nothing will. So why do we bother building larger telescopes? And particularly, I'm certain that this audience has been paying attention to the images that come from the James Webb, and so you might be asking yourself, why, with a brand new telescope just launched in space that's doing spectacular science, is it important to continue building ground-based telescopes? And it is extremely important to continue building ground-based telescopes, but that is what I want to try to answer for you in this talk, one of the things I want to answer for you. And for me, the answer to that question starts first with the importance of astronomy, which we'll get to in just a minute, but the other is the importance for humanity in a much broader sense. And to convey that, I really like to start here, which is the view of the sky over Las Campanas. You can see the observatories, the telescopes that are down there now, right there on that mountain. And I have spent about a year of my life at that observatory, spread over 20 years, 25, maybe, I'm not going to say, more than 20 years. And when I'm there, I still find this view incredibly humbling and awe-inspiring. And I used to think maybe I was just weird, but there is a lot of evidence that I am not alone in finding it that way. And one of the best pieces of evidence is this. These are not just cave drawings of animals. They're actually star maps. And they may have been used to track time or mark seasons, but the one thing they clearly show is a curiosity about the universe around us. And what I find even more amazing than these is this. This is just a sampling of the 150 newspapers that had images from the James Webb Telescope when they were first revealed above the fold on the front page on the day that President Biden scooped NASA by wanting to reveal these images before NASA was able to. So when you're getting scoops by the President of the United States, you know you're doing pretty good science. So the point here is that astronomy really has the power to inspire curiosity in people all over the world, not just scientists. And for just a brief moment in time, in the middle of a pandemic, in the middle of everything else that is going on, this kind of discovery and awe really brings people together. And certainly in the United States, the kind of tour de force capability and technology that enabled these images, I think, brought incredible pride, and I dare say, I certainly hope, it inspired a next generation of scientists. And that is what is important to me, to be perfectly honest. I don't care how many next generation astronomers we get, we're going to get plenty. What I care is that people care about science, become science literate, and pay attention to science. And if these images do that, that is more than enough reason to be building telescopes. But there is a lot more reason to be building telescopes, and that is the incredible impact that astrophysics have on other fields of science. So, first of all, astrophysics, of course, is the study of how physics shapes our universe, but what we learn from telescopes tells us a huge amount about geology, about the Earth before we can observe it, how the Earth formed initially, about biology and the origins of life. And it always amuses me that biology textbooks start with, there were monomers and polymers and they were formed somehow, but then they formed DNA. Where did the monomers and polymers come from? That history is erased on Earth. The only way we're going to know that, the initial conditions for life, for sure, is by studying other planets. Then there's chemistry, the origin of the elements, fundamental physics, and the thing that ties all of this together is that the universe is the ultimate laboratory for extreme environments that we cannot create on Earth. And so if we really want to understand how the universe is shaped, how all of these fields of science are shaped, we need to be able to study what's happening in the universe beyond Earth. So why do we need larger telescopes? The answer starts with this plot. So this plot shows the growth of telescopes over time. You have this diameter of the telescope, which is the size of the primary mirror of the telescope, against time on the x-axis. And each leap in telescope diameter represents a leap in our ability to collect light, and a leap in our ability to understand the universe comes with that increase in sensitivity. So with the first ground-based telescopes, we discovered the solar system. We discovered planets beyond our Earth. We saw moons orbiting other planets. We saw planets orbiting the sun, and we came to understand gravity. Pretty fundamental in the story of our understanding of fundamental physics. In the century after that, we put our sun in the context of other stars and came to understand the galaxy beyond our own solar system. And in the last century, astronomy has taken off incredibly. We've come to understand the physics that powers the sun. We've learned about the universe beyond our galaxy. We've learned that the universe is expanding, and not just that it's expanding, in fact that it's accelerating in its expansion, which is inconsistent with everything we know about fundamental physics. And we describe our ignorance of that phenomenon just as dark energy. We came to understand that most of the matter in galaxies is invisible, and we describe our ignorance of that fact just as dark matter. And we've come to understand that the galaxies themselves often contain black holes, which is another phenomenon that prior to their actual observation in the universe, was just some mathematical phenomenon that was postulated to possibly exist in the universe. So with the next decade and the decades after that, the Giant Magellan Telescope is going to be one of the key tools that we use to understand the new physics we've already discovered and potentially to discover new worlds. And I forgot to mention, one of the other things we've done in the last century is find planets. We're going to talk a lot more about that later in the talk. Okay, so what is so special about larger telescopes? Fundamentally, it comes down to three things. The first is increased sensitivity. That just comes with the increase in collecting area. increased angular resolution, which it turns out also increases with the diameter of the primary mirror, and I'll explain why in a minute. And the third thing is that with newer telescopes and improvements in technology, we can build more powerful instruments. And the particular instruments that we can build for any telescope are determined by the design of the telescope. So there's really a connection there that's fundamental to the design of the telescope itself. So I want to just give you a visceral sense of some of these improvements. So the first thing we're looking at here is the Whirlpool Galaxy, taken with a 1.2 meter telescope at the Palomar Observatory. And when I hit return, you're going to see the same Whirlpool Galaxy observed from HST, from the Hubble Space Telescope. Perfect. You guys did that perfectly. That was just right. Okay, wait for this next one. Okay, so this is going to show you the evolution from the Hubble Space Telescope, which is, again, a 2.5 meter telescope, and it does have infrared capabilities. So I'm going to show you an apples-to-apples comparison of an image of a star-forming region, here with Hubble, to a picture with the James Webb Space Telescope, 6.5 meters in diameter. Again, what more could I ask? The next one's going to be an ah, but you guys will be able to get there. Okay, so the point here is that the James Webb Telescope is 2.5 times bigger than Hubble, which gives it 7 times the collecting area. Because they're both above the atmosphere, they get to the fundamental resolution of the telescope, which is determined by the quantum mechanical limit of how the light itself interacts with the primary mirror. So the resolution of the telescope actually improves linearly, directly, proportionately with the size of the primary. So James Webb, being a little bit more than 2.5 times bigger than the Hubble, can get about a little more than 2.5 times better resolution. And of course, with 30 years in between these two telescopes, the instruments got better. And you might very reasonably be asking, what's the next step here? Are we going to be able to launch a next generation after this? And the answer is that actually we don't now have the technology or the ability to launch larger telescopes than the James Webb Telescope into space. So if we want to do any better than this, we're going to have to build larger telescopes on the ground, and we're going to have to beat the atmospheric turbulence, beat the blurring of the atmosphere, in order for those telescopes to actually get to their best resolution they can offer. So it used to be that we had to go to space to beat atmospheric turbulence, but in the last 30 years, we've developed adaptive optics, which lets us conquer the turbulence in the atmosphere and get to that diffraction limit. Now, the turbulence effect is what you're seeing here. So the hot air coming off, the turbulence in the atmosphere is very similar to the effect you see when you look over a hot road. So you see the heat coming off that road, and it blurs the background objects when you look over it through that turbulence. That's exactly the effect that's causing blurring in this handful of stars that you're looking at when you're looking through a telescope from the ground. So if this represents the resolution limit caused by the atmosphere, which we call that the seeing limit, this image shows you how Hubble would do, which getting to a 2.5 meter resolution limit from space above that turbulence. This shows you a direct comparison with what the Webb telescope can do in that same field of view. And this shows you what we'll be able to do with the Giant Magellan Telescope. So we'll be able to get 10 times better resolution than the Hubble, 4 times better resolution than James Webb. And we'll be able to do that with the much larger collecting area than either of those telescopes, due to the 25.4 meter collecting area and diameter of the telescope from the ground. So what exactly will we be able to do with GMT? Well, the answer is that we will be able to really revolutionize all fields of astronomy, all areas of astronomy. And that is not an exaggeration, but I'm going to give you a quick list of the highest priority science questions that we're expecting to answer with GMT. So first of all, we're certainly going to do exoplanet science, and this telescope will be revolutionary for searching for signs of life. We're going to get into that in a lot more detail. We'll be able to study the collisions and explosions that cause gravitational waves. We're beginning to do that with the current generation of telescopes, but we'll have much more accuracy and ability to resolve those objects as they fade very quickly, so the telescope size is really critical. We'll be able to study the composition and physics governing the universe, the dark matter and dark energy phenomena that I already mentioned. And finally, we'll be able to study directly how the first stars formed and the first galaxies around them. And of course, we know that those first stars and galaxies formed, but because the chemistry was so different in the early universe, the way that stars and galaxies are able to form now does not tell us how the first stars and galaxies were able to form. So while we know they must have formed, we really don't understand how from watching things and stars and galaxies form nearby. And finally, we'll be able to try to understand the formation of black holes, all the way from the stellar mass black holes that we're starting to understand through observations with LIGO, to galaxy mass black holes that are really seem to be at the center of all galaxies. Now, the amazing thing to realize here is that all of these topics, all of these questions build on discoveries that were made with the current generation of telescopes that were unplanned. By which I mean that these are discoveries that were not written down as reasons to build the current generation of telescopes. So the point is, new capabilities lead to unpredicted discoveries. So what I've just given you is a whole slew of excellent reasons to build these telescopes, but we will be learning things that we are addressing questions that we do not yet know to ask. Okay, now I keep saying we are building this. Who is we? Let me introduce you to the partnership. So the Giant Magellan Telescope is a partnership of 13 universities and research institutions around the world. That includes 10 in the United States. It also includes the country of Australia, where we are represented by two institutions, one university and one that represents the rest of Australia. The Korean Astronomical Space and Science Institute, representing all of South Korea. We're also joined by FAPESP, which represents the state of Sao Paulo in Brazil. And by far, without a doubt, our most important partner is Chile. So they are not only hosts to the telescope, that shows you where the telescope will be built, but the operation of the telescope throughout its lifetime is a collaboration with Chilean scientists and engineers who become the heart of the observatory, without a doubt. So I want to especially point out that. I also want to point out that over the last few years, we've joined forces with the other US-led Next Generation Telescope project, the 30-meter telescope, to form what's called the US Extremely Large Telescope Project. Astronomers are very creative. So US-ELTP. And this brings together two very complementary, very different sets of capabilities in these telescopes. And it will let the community gain access to both the north and the southern sky. So GMT reaches up to this line, and TMT will reach down to that line. So we'll get access to the full sky, which is really important, particularly for being able to observe extremely rare objects, like, for example, maybe the first planet that we find that hosts life. We're also joined in this partnership by AURA, which is the Association of Universities for Research in Astronomy. And they'll bring user support and the ability to more rapidly turn observations into published science. They'll increase the access to the telescope by scientists around the community. And we think that is really important because greater participation leads to better science. We see that again and again with every facility we ever build in astronomy and in other fields. The key to all of this is to bring the National Science Foundation in as a partner in both observatories. And that is particularly exciting because these telescopes would represent the largest public-private partnership for research ever undertaken in the United States. So it would leverage the federal investment, it would leverage the private investment. It also enable, as I've already mentioned, much broader participation across the United States, which is obviously really positive both for science and for society. And it would enable the continued strength and leadership of the United States in research, especially astrophysics. All right, with that, I want to turn straight to the telescope. Okay, so this shows you your first close-up view of the telescope here inside a cutaway picture of the dome. So you can see the enclosure here. Again, that's a 22-story building, and you can just begin to get a sense of the incredible engineering feat that is the enclosure itself. Not only does it protect the telescope during the day, but it conditions the environment around the telescope at night, protecting it from wind shake, protecting it from thermal changes, protecting and creating the right airflow over the telescope to allow the kinds of observations that we need. So you also see the telescope itself here, mounted onto its pier, and when I hit return, you're going to get a better view of that. And you can see, just for scale again, a tiny person and a forklift down there. This is what we call the telescope pier that goes straight into bedrock so that it can really anchor the telescope for accurate motion. You see the C-rings, that's this purple structure here, allows the telescope to nod in elevation. You see the azimuth disc, which is a big turntable that allows the telescope to rotate 360 degrees, and in that way the telescope can point anywhere in the sky. You get a better close-up of the telescope here, so there's that azimuth disc, and you can see the beautiful 8.4 meter mirrors that make up the primary. I'm going to tell you how that works in a minute. So this is an optical to infrared telescope. It goes from about 0.3 microns, where the UV, where the ultraviolet light stops being able to pass through the atmosphere. So it goes from that cutoff all the way into the mid-infrared. The primary mirror is 25.4 meters from edge to edge here. Each of these mirrors is 8.4 meters. They're the largest mirrors that can be made on Earth. And the technology for making these was first invented by a guy named Roger Angel at the University of Arizona, and they turned that technology into a mirror lab. It's now called the Keras Mirror Lab. And they make these mirrors, the only place in the world they can be made at this scale, underneath the football stadium at the University of Arizona. It's the only place on campus they could get the space. The mirrors are each, I think I just swallowed a mosquito. Excuse me. Okay, so the mirrors themselves have an accuracy in figure of about 10 nanometers, which is 1/1000th of the thickness of the human hair. And that describes not just the accuracy of the surface of a single mirror, but it describes the accuracy with which all of those mirrors form a single operating surface. So even though there are gaps between them, they are lined up to within 10 nanometer accuracy. Actually around 50 nanometer accuracy, but ballpark. Thank you. I appreciate it. Okay, so each of these mirrors weighs about 18 metric tons. And they collect light and they send it up to the secondary mirrors here, which is where the adaptive optics system resides. So our secondary mirrors, which reflect light back down, you're going to see that in a minute, are 7 mirrors that work paired with the primary mirror, and each of them is about 1.1 meters in diameter. So light comes to one primary mirror, goes up to one secondary mirror, and then comes down and to the focus of the telescope in the middle. And you get a better view of those secondary mirrors here. So each of these is 1.1 meters in diameter, right? So even those are pretty big. And they change shape. What we mean by a deformable mirror is that they change shape thousands of times per second to perfectly take out the turbulence in the atmosphere. And I do mean perfectly on the level of quantum mechanical interaction of light with the primary mirror so that we can reach its best resolution limit. And again, the shape accuracy has to be about 50 nanometers. Now let me show you how each of those mirrors works. So the idea is that first we need to be able to measure the turbulence of the atmosphere, and we do that by looking at a reference star. So that reference star sends us, we see from that star wave fronts of light that have been damaged, warped by the atmosphere. Let me keep this playing. And that warping we measure, and we put the mirror surface, we put the exact opposite shape onto the deformable mirror so that when light reflects off it, it perfectly corrects those wave fronts. So let me show you what each of those mirrors looks like close up. So this is an example of an earlier generation of that deformable mirror technology in what we call an adaptive secondary mirror. So what you're actually looking at here is a 1 millimeter thick deformable mirror resting on a foam pad. So that 1 millimeter thick mirror is the deformable mirror surface. It's got a bunch of magnets, about 700 in fact, glued to the back surface, And those magnets attach the mirror to this rigid, what we call rigid body or rigid structure, against which these actuators can push to reshape the mirror. So this deformable surface is configured and positioned by those 700 actuators. And each of the 7 secondary mirrors in our secondary mirror system is an assembly like this. So together they have 7 times 700 actuators. Okay, the last thing I've mentioned, of course, is the instruments that allow you to reconfigure the light that the telescope collects, forms into perfect images, but then the instruments have to reconfigure that light into images and spectra so that we can record the light and measure it so that we can actually do the science that we want to do. So what you see here, as I hit return, is the light coming to those primary mirrors, to the secondary mirrors then, and now you're seeing a cutaway which shows you where oops, I went backwards, that shows you where those instruments are located. And you're seeing a still here, so maybe that won't be quite so jarring. And you can see the instruments on a big cassette, this big cylinder that rotates in the middle of the telescope. It's going to blow up here so you get a little bit better view. So those cameras and spectrographs have all the complexity of your cell phone, but they're about the size of 20-foot shipping crates. Just like the storage pods that you see around your neighborhood in people's driveways, that's about the size of one of our instruments. So I've already mentioned the design of the telescope dictates what kind of instruments you can put on the telescope, but our telescope is designed to take everything from infrared cameras and optical cameras that can take and record images of things like this, which is a cluster of galaxies at large distance, sort of halfway back towards the Big Bang. I'm going to talk about what that means in a minute. We can take spectra. This is a picture of what spectra of individual stars look like, and we can combine those two concepts so that we can take dynamical images, so that we can take spectra and turn them into images so that we can understand the dynamics of a galaxy, which is what you're seeing here. This is a spiral galaxy viewed edge-on, so you're looking along like the pancake of the spiral galaxy, the disk, and the side that's coming towards you is blue, the side that's going away from you is shown red. So this just gives you a sense of what the cameras and spectrographs that we use can do. Okay, so now I want to get straight to telling you about just a couple of the most exciting science problems that we're going to do with this telescope. And we're going to start far away, so we're going to start in the early universe, trying to understand the formation of galaxies and what we call structures of galaxies, structures between not just the structure of a single galaxy, but structures of galaxies that form sort of the cosmic web of things that we see out there. So I want to start with this close-up image taken of the Hubble Deep Field. And what you're seeing here in this image is about 100 million times fainter than you could see with the naked eye. The faintest objects are much less than 1% of the brightness of the night sky. And some of the galaxies that you see here, so first of all, almost everything you see here is a galaxy. I don't think there are any stars in this image. Oh, there may be one star. That might be a star. Everything else is a galaxy. Some of these galaxies look faint because they're intrinsically faint, meaning they just are low mass and they don't have many stars in them. But some of them are faint because they are very distant, and you know intuitively that things become fainter when you're looking at them over large distances. And that's what we mean when we say this is a deep image. We're looking at some of the most distant objects that we've ever seen in the universe. And when I hit return again, what you're going to see is some of the most distant objects in this image. And these are actually galaxies that are about 13 billion light years away. And what that means is that the photons that are coming to us from these galaxies have been traveling for 13 billion years. The speed of light is finite. So if these are distant enough, it takes billions of years for the light to get to us. But the other point is that we're looking back in time. These are snapshots of galaxies in the first few hundred million years after the Big Bang. So we're looking at baby pictures of galaxies. And another thing that's important to note is that it's not random that these are red. So these are red because of Doppler shifting. So as the universe expands, it literally stretches the light. And Doppler shifting, you're familiar with the effect with cars, right? When a car goes by, you hear, right? That's Doppler shifting. So the frequency of sound waves is getting stretched because the car is moving away from you. It's the sound waves are literally being stretched as that car recedes into the distance. Light, the same thing happens to light when the universe is expanding. And so the galaxies that are at very high distance are literally shifted, the light from it's literally shifted to redder wavelengths. Okay, so this compares the universe as seen by Webb versus Hubble. And obviously this is Webb, and that's Hubble. Okay, so the very first thing you see from this image immediately is many more galaxies than we expected. The second thing you can see almost immediately is that some of what we call grand design spirals, these spiral galaxies that look perfectly formed, were actually formed and appear much earlier than the universe than we even expected. And we were surprised when we saw how early they were forming with Hubble. So now we are even more surprised. And the very exciting thing about that is that our models need work. There's a lot to be left to learn. So that is incredibly exciting. But the point that needs to be made here is that we can't learn what we want to learn yet, because in order to take spectra, you need much more light than you do just to take a picture. Because when you're taking a spectra, you're dividing up the light into very small wavelength bins. And if you want to do that accurately, you need more light. You need greater collecting power. So this shows the synergy between ground and space-based telescopes. So this shows the current generation of telescopes compared to the size of Hubble. Hubble was used to find the galaxies. The much larger ground-based telescopes were needed to take the spectra once the galaxies were found. If we want to take spectra of the objects seen with Webb, in many cases we are going to need the much larger ground-based telescopes that we are currently building. So if we want to make good on the promise of the science that can be done with the James Webb Space Telescope, we need a next generation of ground-based telescopes. And this shows an example of what we can do, what we'll be able to do with GMT. So first I'm showing you zoom in on the Hubble Ultra Deep Field, zooming in here and zooming in again on just one object. If this shows you what you can do with the current generation, this shows you what you'll be able to do with GMT. And it's a little counterintuitive, but the other thing that's very powerful about the Giant Magellan Telescope is that its wide field of view will actually help, even for understanding galaxies at very large distances. And so the reason that's important, so first let me point out the field of view. So this is the Giant Magellan Telescope's field of view compared to a very familiar object on the sky. This is more typical of very large telescopes, and particularly of the next generation telescopes. So GMT will have not just the ability to resolve these individual objects very accurately and take their spectra, but we'll be able to study many of them at one time within this wide field of view. And the reason that's so important is illustrated here. So to go from just counting and seeing and finding the galaxies initially, to actually understanding them, we need to be able to take those spectra, to study them in more detail. This is one field of view with JWST, and so this is a whole slew of images taken with the Webb telescope. And what I'm trying to point out here is that a galaxy that is this high redshift and this rare is not common on the sky. It's actually very rare on the sky. So this shows that field of view compared to the GMT field. So if we want to be able to study these galaxies efficiently, what we really want to be able to do is study many of them at once. So having a wide field of view allows us to take spectra in individual locations in the sky and study these galaxies efficiently so that we can get statistical samples, not just of the most distant galaxies, but of galaxies nearby and everything in between. And the reason that's so important is because we don't have the luxury of watching a single billion-year-old galaxy evolve the way biologists can watch a child become an adult. We're trying to piece together the snapshots at high redshift with the galaxies we see nearby today, with everything in between. And so we really do need to be able to study these galaxies efficiently at very high resolution to put together a picture that tells us how galaxies formed, how they're affected by dark matter, dark energy, the black holes at their core, and understand all of the questions that I've already mentioned. All right, so now let's come a little closer to home. Let's talk about planets. So 30 years ago, we had no proof that there were planets beyond our solar system. You might have guessed that we weren't unique in the universe, but we had no idea how to prove that. We had not detected a single additional planet beyond the solar system. Now we know of over 5,000 planets. We've measured them, we've detected them without a doubt. What's even more amazing is that hundreds of those planets that we've actually seen are in the habitable zone, I'm going to take that number off, are in the habitable zone around their parent star. That means that they are just the right temperature, the right distance from their parent star to have liquid water, which we believe is key for allowing the chemical mixtures to create those first monomers and polymers and lead to life. You need a soup in which those chemical interactions can happen. So from those hundreds that we've actually observed, we can tell that if you extrapolate from what we've seen in the local, in what we call the solar neighborhood, people like that expression, but it's what we actually say. From what we've seen in the solar neighborhood, we can extrapolate to 40 billion potentially habitable planets in our Milky Way alone. And that, of course, just leads to a whole slew of more questions, which I'm just going to list some of the top ones here. So first, how do planetary systems form, including our own? So I already mentioned, the early stages of the formation of the Earth are erased by what's happened on Earth since then. If we want to understand how our Earth formed, how it came to be a rocky planet with water, how it acquired water, we need to study other planetary systems. How common are rocky planets? It turns out that rocky planets like our Earth are actually quite rare, which is extremely surprising. We usually like to assume in astronomy that there's nothing about our place in the universe or our particular condition that is unusual. But it does turn out that rocky planets the size of Earth are not common. Do any of the nearby habitable planets actually support life? We'd like to be able to determine that definitively. And finally, if we're going to determine that, how will we definitively recognize the signature of life on other planets? This is just a handful of the questions we need to answer. Okay, so a very key technique to being able to answer any of these questions is direct imaging of exoplanets. And I do not mean that we can produce the kinds of images that you saw in the artist rendition on the previous slide. The kinds of images we can take are exemplified by this. So what you're seeing here is a movie of individual observations taken, in this case with the Keck telescope, but the current generation of telescopes are all making similar cutting-edge observations like this. But what you're seeing, the technique used here is very similar to if you were going to try to see a faint object in the sky, like a bird, next to the sun. You would mask it out with your hand so that you could see the much fainter object. You mask the bright object to see the faint one. So that's what's being done here. You mask out the bright star at the center with what we call a coronagraph, and then you can see the much fainter planets around it. So on the right, what you see is a still shot of a nearby planet called Beta Pictoris b that shows sort of the current cutting edge capability in terms of exoplanet imaging. Now, this planet turns out to be about 10 Jupiter masses, and when I click return again, you're going to see how we would be able to observe this system with GMT. So seeing the 10 Jupiter mass planet would be easy. We'd be able to see smaller planets at even much smaller separations, all the way down to about a half a Jupiter mass in this particular system. And the reason that that is so important is that once we can image the planet, we can take multiple images of it in different wavelengths, start to measure its density, its radius, its temperature, and start to understand its atmosphere. And we can feed that light into a spectrograph to study its atmosphere in detail. Now, many of you who are paying attention to the observations made by Webb know that they are also able to do this kind of thing. They're a 6.5-meter telescope. The observations I just showed you from Earth are made with 8-meter telescopes, so it should not be a surprise that the Webb telescope can do this too. But a really key point to realize is that all of the planets that we've observed this way are young. Why is that? Young planets are hot. They're still hot when matter collapses. It turns kinetic energy into thermal energy. And so young planets are still radiating away the thermal energy from their own formation. That makes them obviously hot, but that also makes them bright in the thermal infrared. That is why they are the easiest planets to observe. That's great, but if we want to understand old planets, we need to be able to, if we want to study how planets form and really evolve, how the planetary systems beyond the first few million years of formation evolve, we want to understand how Earth got water, we want to look for life, we need to be able to study planets that look like this. This is not a planet that is radiating, that is hot in the thermal infrared. It's nice and cool. It is friendly to life. It is old. Life has had time to form on a planet like this. So, old, cool, faint. And we can only view it, it's not visible in the thermal infrared. It can only be observed in reflected light, which is what we're all accustomed to seeing in the moon, or in a picture of the Earth as viewed by the moon. And that explains, in a nutshell, why ground-based telescopes, in fact, why the Giant Magellan Telescope is so key, and why it is so synergistic with the James Webb Telescope. So the Webb Telescope is fabulous at observing hot young planets at larger distances from their parent star, and it observes in the thermal infrared. It starts to get much less sensitive down at the shorter wavelengths, and in the optical, it can't really make observations at all. It's not designed to work in the optical, it has no detectors in the optical. The Giant Magellan Telescope is designed primarily to work into the visible, and then it has reduced sensitivity as you go farther and farther out, especially into the thermal infrared, where the Webb telescope is ideal. So the other really important thing about having access to the optical part, the visible light part of the spectrum, is that that is the part of the spectrum where oxygen can be observed. Now let me show you why that is so important. Okay, so this is a complicated plot, but let me break it down and explain it. So if we want to find planets with life, what we really want to do is find the combination of molecules that can only be produced by life, because many different kinds of combinations can be produced by geological methods, geological sources. So what's shown here is different combinations of the same molecules that can result on 3 different descriptions of planets as a result of the geological activity on those planets. There's only one combination here shown that has molecular oxygen that is a combination that can be produced by life. So what we're looking for is that special combination that indicates a biosignature, indicates that the combination of molecules and the gases in the atmosphere of a planet had to come from life. Not necessarily little green men, but at least plant life and bacteria. Maybe little green men, who knows? All right, so I hope I've convinced you that we need this telescope. Now what I want to do is tell you where we are in the process of building it, because we have made a lot of progress. So what you're seeing here first is the final design of the telescope. The design is complete. You can see a bunch of cool structures here that I've pointed out so far. You can see the azimuth disk. You can see those C-rings. Where is the C-ring? You can see the C-ring here that the telescope nods up and down on. You can see the upper support structure that supports the secondary mirror. And here you see a cutaway of the telescope structure so that you can see where the instruments are supported. The telescope is actually being constructed at Ingersoll Machine Tools in Illinois. And in order to have enough space to do an assembly, a factory assembly of the telescope before we take it apart again and ship it to Chile. They had to build us a whole new building. So you can see that building in the midst of construction in about 2022. Here you can see the building as it's complete. And I've circled here a couple of people for scale. And they are actually quite far back because I have stood at this railing and it is not a normal railing. It comes up to about here. So that is a giant pit, and what that pit represents is actually, it's sort of the factory version, you could say, of the top of the telescope pier. So they'll build the mechanical structure of the telescope on the top of that cement structure to test out the fabrication. And I think this is incredibly exciting to see. This is the beginning of the fabrication of the azimuth track. You can see the large structure over here, and here you can see the heroes that are doing the welding of this azimuth track. Just, I think, in the last month, and that's at a factory very near the one I was just pointing out in Illinois. Okay, here you see the adaptive secondary mirror, an exploded view of the design of that secondary mirror. So this shows you, just to give you a sense of the complexity of the machine that is behind each of these 7 secondary mirrors. And I just want to call out the deformable surface itself and the rigid structure against which that deformable surface is stabilized as it's refigured. So what you're seeing here is the 1 millimeter surface, 1 millimeter thin glass sheet before it gets coated, sitting on top of a big chunk of glass, because obviously you don't want to push on a 1 millimeter unsupported piece of glass while you're polishing it. So this is how it gets polished. What you're seeing here is the metrology of that surface to make sure that it was made correctly. And here you're seeing the rigid reference body against which those actuators can be stabilized as they're repositioning the deformable mirror. Okay, this is one of our absolutely gorgeous primary mirrors. The first 3 segments are complete. And what I want to show you now is snapshots of the process for building these mirrors. So I already told you these mirrors are made in the Karas Mirror Lab underneath the football stadium at University of Arizona. To make these mirrors, they actually construct an oven around the mold for the mirror. First they construct the mold, they construct the oven around it, then they place the glass, and then they spin the entire oven so that as the glass melts, it takes on a parabolic shape so that you don't have to remove inches and inches of glass in the polishing process. So when you start polishing the mirror, it already has approximately the right shape. Okay, so here you see the process step by step. You can see them just beginning to build up the mold for the mirror here, and they actually construct the oven around the mold. And the pieces of the mold are hardened styrofoam. So they're rigid and they can be tough, but you can't just throw the glass onto those molds or they would crack. So after you get the mold constructed, you have a bridge that comes out, and you carefully place the glass piece by piece, which is what you're seeing here. You see the mold underneath, the glass is in the process of being placed by people who stand out on that bridge. Once all of the glass is placed, they build the rest of the oven around the glass, they close the lid, and then eventually they can spin the entire oven to melt the glass. So you see the glass placed in the mold, fully filled here. Next, you're going to see the oven lid coming down. There's the oven lid, and here you can see the glass in the process of melting. So you see it beginning to become fluid on top, and you can see that it's starting to flow into the cracks of the mold. You're going to see that becoming a perfectly smooth surface, and then you can imagine that that oven is spinning around fast enough that the surface of the glass takes on a parabolic shape. Now where you see it dark is where the glass has melted and is flowing down in between the pieces of the ceramic mold. So instead of being a 3-foot solid chunk of glass, it's light-weighted by virtue of being partially filled with this ceramic that can be removed after the glass is cooled and comes out of the oven. Here you see the bare glass with the oven gone, and you can see a fixture that's going to come down and be attached to the top of that glass. And when they lift that up, that is a good day to be sedated. That is terrifying. Then they pick up the mirror and they put it into a handling fixture where it can be worked and figured for almost 2 years to make the final mirror. So here they are moving the mirror, and that is an image that makes me completely nauseous. But eventually they're going to get it into the cell where it's safe and it can be stood up on end, which is what you're seeing there. That gives them access to clean out the back of the mold, which is what you're looking at here. So they remove all the ceramic from the back of the glass. You can see what that looks like here. And when they get that all cleaned out, what they're going to be left with is just the honeycomb structure of the mirror itself with no ceramic. And you're looking at the front side of it there. So this shows segment 3 under the polishing lap, and that's going to go around and around for over a year to make the perfect, pristine mirror figure that we need. And what you see on the right is segments 4, 5, and 6 in storage. Segment 7 is being cast as we speak. So this is just to give you a sense of the complexity of the machinery that supports the mirror while it's on the telescope, so that when it's pointed to the horizon or to zenith, you still have the correct shape for that mirror. So what you want to do is be able to keep it in the perfect shape as the gravity vector changes. So these structures, everything you see here, the load spreaders, actuators, push and support the mirror so that it doesn't distort as the telescope moves around the sky. It also has to also have to maintain the right temperature on the mirror, so you see a heat exchanger to control the thermal environment. And this picture I love because this shows the weldment that is the mirror cell in its early stages of being fabricated. This shows it about half populated with electronics and the actuators that are needed. And finally, you see it at this point in its safe for glass configuration. It's just passed its final test and will accept a mirror segment for figure testing at the mirror lab. Finally, I want to show you the enclosure. Now you can see a couple of other key features here on the summit. You see the utility building, which allows the machinery that produces heat and causes vibrations to be housed away from the telescope, where that heat and vibration is not going to bother the observations. You can see the summit support building, where the mirrors are going to be re-illuminized throughout the life of the telescope to keep them clean and super shiny. And from this next simulation that you can see here, you can get a sense of the complexity of the design of the enclosure. So this is a computational fluid dynamics simulation that analyzes the airflow around the telescope itself so that we can minimize the turbulence in the dome. So the blue shows calm air, the red shows turbulent air. We started this work with Boeing, and now we continue these simulations on our own. And the point of this is just to give you a sense of the kind of detail that goes into the planning and design of the enclosure that houses the telescope. And I want to call your attention one more time to the layout of the summit so that you can see the structure where the mirrors get coated again. You can see the enclosure and the utilities building, and you can see, by comparison with this image, what the summit looks like today. In this picture, you can see the foundation that we've already dug for where the pier will be. That's that center circle. You can see the outer ring wall of the enclosure where the foundation will be that supports the rotating upper structure of the enclosure. You can see the utilities tunnel that's been dug to allow the utilities to go from the utilities building to the telescope. And finally, I just want to leave you with this image of the observatory in operation. And I want to thank you, as Dan said, because it's people like you that let astronomy continue to get the support it needs to keep doing cutting-edge science in the United States. So I want to thank you for coming and for listening.